I probably should have gotten Zoom set up a little bit more nicely. Let me first make sure there's nobody else in the waiting room, and for some reason that came up instead, so I'll go on and get started. 5 here, and it just looks like it's the 3 of us here. Yes, I can. Brandon? Okay, good. Okay, let me ask this. How did you turn it in? Emailed it. Okay. I am way behind on emails right now, just because we were out of town last weekend, and the where we were had absolutely terrible email service. I mean, terrible. So I couldn't get on it, and then we drove back Monday morning, and it's just been horrendous ever since. So anyway, I probably did get it, but I haven't printed it yet. But while we've been talking, we've also had Jordan and Ashton come in. So we have perfect attendance today. Way to go, folks. And so let me clear this out of the way. And I would go and check on email right now, but we're already running a little late, so I'll try to check on that. I have 2 hours office hours this afternoon. Don't have right now any scheduled appointments in the virtual advising center, so I hope to be able to get some of the things caught up this afternoon. Won't know for sure if I'll get it done, but I'll do my best to get that done. And then I think I'll be able to work into the evening some today too. Yesterday it was very hard. I was going to try to do more in the evening, but I got captivated by some of the election returns and really disappointed in many of them. So anyway, that's how it goes. So I'll try to check on that and make sure I've got it. All right, let me get the slideshow set up from the current slide. We are recording. I think everything's in order. So let's get going. Any other questions today before we get going on section 8.5? All right. We're in chapter A, integration techniques and improper integrals. And just to give you a perspective on this, 8.6 is numerical integration, so we will do that, or at least throw it a little bit. And 8.7 integration tables. This is a long chapter, okay? And then we have improper integrals, and if it's just the same to you, I think we'll just do a slideshow of that one, just so you'll be exposed to it, and then move on from there. So we'll just go through 8.7 as far as testing purposes, but I will do a slideshow of 8.8 just to give you an idea on that. Okay, so we're in chapter 8, integration techniques, and that's basically, we'll stay with that. Won't do that much with improper integrals, though I will show them to you. And then we're in 8.5 today, 8.6, 8.7, then we'll have our test on chapter 8. Sound okay? Okay. 8.5 is what we call partial fractions. The objectives in this section are to understand the concept of partial fraction decomposition. It sounds like it's sort of falling apart, doesn't it? We'll use partial fraction decomposition with linear factors to integrate rational functions, and then we will use partial fraction decomposition with quadratic factors to integrate rational functions. Now, if you haven't picked up on it yet, notice here, we're dealing with rational functions in the integrand. What do we mean by rational functions? Well, first 5 letters of rational are ratio. So that means there's some sort of division going on. Okay, what are we dividing? Well, what we call rational functions are ratios of 2 polynomials. Okay, so the things we had with square roots that was a ratio, but it wasn't what we call rational functions. So that was stuff we've already covered. This is just going to be ratios of polynomials. And how do we handle those? Okay. Now, a procedure for decomposing a rational function into simpler rational functions to which you can apply the basic integration formulas is called the method of partial fractions. Okay. Now, to see the benefit of the method of partial fractions, let's consider this integral. Okay, now this is a ratio of two polynomials. The numerator is a pretty simple polynomial, 1. That's it. The denominator is a polynomial, x squared minus 5x plus 6. Okay, now, what if we were integrating that? Well, you can't do a substitution, use substitution, that won't work. You could conceivably complete the square and then try to move in that direction. That's really awkward. Doable, but awkward. But here's what we mean by the method of partial fraction decomposition. Okay? What we're going to do here is notice that this denominator can be factored. Okay? And that factors as x times x. That's what gives you your x squared. Look at the sign of the last term. It's positive. That means these two signs have to be the same. Okay? And since the middle sign is minus, they both have to be minus. Now we look for a number that multiplies to be 6, adds to be 5. 2 and 3. Okay. Now, all we've done is factor that denominator. Now here's where the magic comes in. Let's take that integrand in factored form and see what we've got. 1 over x minus 2 times x minus 3. Okay? Now, we'll worry about the dx part a little bit later. Okay, now, that is a fractional form, okay, a rational expression, okay? Now, it seems like that it should be able to be broken down into two partial fractions. One of these would be, say, some number a over x minus 2 plus some number b over x minus 3, okay? Because anytime you're adding two fractions together, different denominators, you can multiply the denominators and come up with, you know, least common denominator, that kind of stuff. So here's our hope that maybe we can do this. Now, this is how we're going to start these problems, and this is how we're going to carry them out. That is an equation we hope is one that's solvable. Okay, we just don't know what a and b are, but we're going to try to figure them out. So how do we do that? That's an equation now. Equations can be solved by, and we're not looking for x, we're looking for a and b. So we're treating x as if it's just part of the problem. Okay, and how we can solve for a and b is multiply both sides of the equation, every term on both sides, by our least common denominator, which of course is this. So we're going to multiply this side by x minus 2 over x minus 3. We'll multiply this term by x minus 2 times x minus 3. And we'll multiply the last term by x minus 2 times x minus 3. Okay. Now what happens on the left-hand side? The x minus 2's divide out to be 1, x minus 3's divide out to be 1, so all you've got over here is just that number 1. Okay, here we have an x minus 2 and an x minus 2 that can divide out, and an x minus 3 and an x minus 3 that can divide out. Okay, now that leaves us an equation that reads like this. 1, that's all you got left on the left-hand side, is equal to a times x minus 2, no 3, I can't read my writing there, plus b times x minus 2. Now, remember, we're not solving for x at this time. We're solving, and I said b and didn't write it down, did I? We're solving for a and b. Okay? So if this equation is true, it should be true for any value for x. Okay? Now this is the part to me that gets a little shaky theory-wise, but it works, and it always works. So here's what we're going to do. Let's first pick some value for x that's going to make that really simple to deal with. And this first one would indicate, let's let x equal 3. Okay? So if you let x equal 3, what we have on the left-hand side is 1, because 1 is 1. It doesn't depend. If x equal 3, 3 minus 3 is 0, so this doesn't give us anything. And over here we have 3 minus 2 is 1, so that was just going to be b. Guess what? There's our value for b. b is equal to 1. Okay? Now that works so nicely. Let's do it again. This is let x equal 3. And the next time we're going to let x equal, guess what? 2. And when you plug that in, you still get a 1 on the left-hand side, is equal to 2 minus 3 is a minus 1, so that would be a minus a, and this would of course be 0. So guess what? This implies that a is equal to negative 1. All right. Now, if we did everything right there, our new integral would be the integral of, remember, this left-hand side here that started off being 1 over x minus 2 times x minus 3, which is the factored form of this, that our a was negative 1 and our b was positive 1. So I'm going to flip the order, if that's okay with you, and I'm going to do equal to the integral of 1 over x minus 3, that's the b part, dx, that's where the dx comes back in, minus the integral of 1 over x minus 2 dx. And guess what? Those are pretty simple integrals to do. What's the antiderivative of 1 over x minus 3? That would be, if I could get my pen to show up somewhere, there it is, the natural log of x minus 3. Okay? The second integral would then be minus the natural log of x minus 2. Okay? And then you'd have a plus c if you wanted to have that. Or you could even say it was log c, or whatever you want that constant to be. Now we can redo this. The log of a difference is the difference of two logs is the log of their quotient. So you could write this as, if I could get my pen to show up again, the natural log of x minus 3 over x minus 2, and then you could have this to be either a log c or a c or whatever. But that would be our answer. Okay? Now you could leave it in this form right here. That's a perfectly good, legitimate form, or this form, or if you had made that a log c, then you would have multiplied the c times right here. C times x minus 3, the log of c times x minus 3 divided by x minus 2. I don't think the book carries it that way, but it's doable. You could have done it that way as well. It's a different c from the one we have there. All right, now that's how I did it. Let's see how they proceed. To find this integral without partial fractions, you can, like I said, complete the square, use the trigonometric substitution, and it's a pain in the neck. I mean, it's there, okay? But it's certainly doable, okay? A real big pain in the neck, okay? I'm trying to, okay, wow. You take half of the b term, that would be 5 over 2, square it, and you get 25 over 2, and then, but you've added that, so you have to subtract it, and it's a really big pain in the neck, okay? And you carry it on through, and ultimately, after a long process, you get down to log of x minus 3 minus log of x minus 2 plus c, which is exactly what we got in fairly short order. Fairly short order, okay? Now, they didn't take it that next step, but they left it there. Now, suppose you had observed that, what we observed, that this could be broken down. Now, they didn't show you how to break it down. They just said this is what it becomes. That's not very fair of them. But if you had known that, then you break that down into two integrals, the log of x minus 3 minus the log of x minus 2 plus c. Much easier, shorter, quicker, in every type of way, better approach to solving the problem. Okay. Completing a square is usually a really difficult, time-consuming, easy to make mistakes problem. Okay, go this way. Okay, that method is clearly preferable to trigonometric substitution. Its use, however, depends on the ability to factor that denominator and to find those two partial fractions that you needed, 1 over x minus 3, negative 1 over x minus 2. Now, here's something I hope you do know. We know from algebra that every polynomial with real coefficients, they don't even have to be integers, real coefficients, can be factored into linear and irreducible quadratic factors. Okay? That's something that I'm not absolutely certain everyone's convinced of, that you can do that, but it is indeed the truth. Okay? Now, here's a polynomial. Okay? X to the 5th plus x to the 4th minus x minus 1. Okay, now that's fairly easy. I don't know why they gave you such an easy one, but this is a 4-term polynomial. If I could get my pen to show up somewhere. I don't know why. Oh, nope. Okay. Okay, here we go again. All right. Where is my pen? There it is, somewhere way down there. Okay, here we go. Now, this is a 4-term polynomial. One thing we could do is factor by grouping. Group those two together and group those two together. That's not a factorization, that's just a grouping. In the first group, we can factor out an x to the 4th. What does that leave us? X plus 1. Okay, in the second group we can factor out a minus 1, and that would leave us an x plus 1. Okay, well, now we have common factor here, x plus 1. Factor that out, and what do you have left? X squared minus 1. I mean x to the 4th minus 1. Well, that is a difference of two perfect squares, so that would be x plus 1 times x squared plus 1 times x squared minus 1. Okay, that gives you x squared, x to the 4th minus 1. But this one can be factored further. So you have x plus 1 times, this one cannot be factored any further. The sum of two perfect squares can never be factored any further. Not in the real number system. In complex numbers, yes, but not in the real number system. So leave that alone as x squared plus 1. That's a quadratic factor. We can live with that. And this becomes x plus 1 times x minus 1. Okay? Now when you put all those together, you see that you have two factors of x plus 1. So that would be x plus 1 squared times your x squared plus 1 times an x minus 1. There is your complete factorization of this polynomial. So if that had been in your denominator, this is how you would have factored it. Okay? And that's what they got here too. X minus 1 times x squared, x plus 1 squared plus x squared plus 1. That term. Now, the x minus 1 is a linear factor. The x plus 1 is a linear factor, but it has a multiplicity of 2. Repeated linear factor. This is a quadratic factor that cannot be reduced to linear factors. So we call that an irreducible quadratic factor. If you can get down any polynomial into a combination of linear factors, whether they're repeated or just single, or irreducible quadratic factors, you've got it. Excuse me, you've got it knocked. I'm sorry. I'm still running so low of energy. I think the anemia is better. Okay, I hope it's better. I feel better. My little things that I have to check on, I wear a Fitbit watch, and so it measures my sleep issues, you know, and stuff. And back when the anemia was at its worst, my resting heart rate was just climbing like crazy. It normally was around 59 or so, you know, on a good night, and it went up as high as 73. I mean, that's a huge climb. And then recently has been coming back down. Not back to 59 yet, but I believe I'm around 63, 64. I don't remember now what it was, but it is coming back, which I take it as a good sign that maybe the anemia is getting better. I'm not having to pump as much blood to try to get the oxygen where I need to get it as I did before. So, but I'm still running out of energy awfully fast. So hold on just a moment. So sorry, but I am literally just, I don't know. I wish he hadn't told me I was anemic like I was. I probably would have thought, well, I'm just old, you know, but now I've got a reason to be tired, and that's what it is. Okay, so this is how we do a partial fraction decomposition. If that had been in a denominator, we would have it knocked. Okay, now using that factorization, you can then write the partial fraction decomposition for any rational expression. Now this n of x is a polynomial function. Now what's required of that polynomial function? It has to be lower degree than your denominator. There was that denominator, so this has to be the numerator has to be degree 4 or less. It could be 1 like we had before, just a constant. It could be an x squared, an x cubed, it could be anything, okay, up to a 4th degree polynomial, a polynomial of degree less than 5. Now, whatever that polynomial is, it has to be degree less than 5. If it's not less than 5, if it's 5 or more, then you do a polynomial division. You divide this into that, you'll get at least an x term or a constant term plus then something. Your remainder will then have to be less than 5. Okay, degree less than 5. So if you have this numerator 5 or more, degree 5 or more, divide first. Get it into a denominator where the or what they call an improper fraction, a proper fraction, where the denominator is the degree greater than the degree of the numerator, then you can go for it. Okay, so if this is a degree 5 less than 5, not 5 or less than 5, then break this. Okay, the linear term is going to have a constant coefficient. The product, the multiple linear term, will have a b over x plus 1 plus another c over x plus 1. Because these are linear terms here, you only have constants above them, 1 degree less. But this quadratic term here, it could have a dx plus e. It could have a x to the first power and then an x to the 0th power. So this would be your breakdown of what the possibilities are here. Now, let's just point something out to you. You would proceed from this point on, multiply by your least common denominator, which is x minus 1 times x plus 1 squared times x squared plus 1. Multiply this by that, you wipe out the entire denominator and just have your n of x, whatever that is. Okay, degree less than 5. When you multiply this by that same thing, you lose your x minus 1 and you have x plus 1 squared times x squared plus 1 up here. Here you'll have an x minus 1 and x plus 1 to the first power and then x squared plus 1. Over here you lose the x plus 1 squared and have x minus 1 times x squared plus 1 as your factor here, and then when you multiply everything here by the product of all those terms, your x squared plus 1s will go away, and you'll have a dx plus e times a x minus 1 times a x plus 1 squared, and you got a lot of work to do. It's usually not as bad as it sounds, but you will have a bit of work to do. Okay, we'll use some of the same techniques we did before, at least for a little bit. Things will start falling apart, but for a little bit you will be able to use it. Okay, so all that blah blah blah, if you turn to page 551, you'll see this sort of summary statement here. Okay, how do you decompose a rational expression, which is a ratio of one polynomial divided by another polynomial? That's your rational expression, into partial fractions. If that degree of the numerator is greater than or equal to the degree of the denominator, divide. We call that an improper rational expression. When the degree of the numerator is greater than or equal to the degree of the denominator, divide first. Okay, so when that n of x over d of x is an improper fraction or rational expression, that is, the degree of the numerator is greater than the degree of the denominator, then divide, and you'll get some polynomial. It could be a constant, it could be a first, second, third order polynomial, whatever it is, plus some new numerator whose degree is less than that of the denominator. It's just like when you're dividing numbers. If you happen to divide and wind up with a fractional form that is greater than the divisor, keep dividing. Okay, that's what we call improper fractions. This is an improper rational expression. Degree of your n sub 1 will then have to be less than the degree of d of x. Apply then steps 2, 3, and 4 for the proper rational expression here. You integrate this polynomial just like you integrate any polynomial, and it's a pretty easy process. Now, once you've got that done, okay, factor the denominator. Completely factor the denominator into factors of the form px plus q raised to the nth power. That's a linear factor raised to an nth power, and ax squared plus bx plus c raised to the nth power. That's a quadratic factor raised to the nth power. Okay. Now, for those linear factors that you have here, that will then break down into, now, remember that's, you have m of them. So the first one's going to be just a constant over px plus q. The second one will be another constant over px plus 2 squared. The next one will be another constant over px plus 2 to the third power, and you keep going until you get to the nth power. But it's always constants in the numerator and multiple factors in the denominator. Started with 1, 2, 3 up to m. Okay, so that's how you deal with the linear factors. When you have those quadratic factors, then you put a linear numerator. Always your numerator is 1 degree less than your denominator. It has to be at least 1 degree up here. If it isn't, you divide. When you get down to doing your partial fractions, it will always be exactly 1 less than the denominator. Occasionally it will be less than that, but you set it up as if it's 1. So that would be a constant over a linear, constant over linear raised to a power, constant over linear raised to a bigger power, always a constant over linear. Or when you get to your quadratic factors, that will be a linear numerator, b1x plus c1, over your quadratic form, and that would be to the first power. Remember, it could be to the nth power here, plus another b2x plus c2 over the that quadratic form to the second power, and you keep doing that until you get b sub n of x plus c sub n over ax squared plus bx plus c raised to the nth power. Okay, a lot of blah blah blah. Okay, easier, I think, to work with than to try to say memorize or get all this down. So let's move on to dealing with our linear factors, the fairly easy one. Okay, all they're asking for now is not an integration, but write the partial fraction decomposition for that. Hey, does that look familiar? We've already done it. We found that broke down to 1 over x, was it minus 3? Yeah, minus 3 minus 1 over x minus 2. We've already done it. We did it earlier. Okay, so let's just watch them do it. Okay, because this is a quadratic that can be factored into 2 linear factors, you should include one partial. Okay, I think, oh, I've got to close my door. Hold on. Howdy. Okay, you got it. Thank you. Okay, our cleaning lady just arrived. She said she'd be sometime this morning, so I try to keep the door closed because I don't have my mask on. She had hers on, but we'll go this right. Okay, so you factor that denominator, and that one factored very nicely. Okay, you can just do it the standard way of doing. If you can't get it to factor that way, you can always use the quadratic formula to factor, and you may wind up with radicals here or there or whatever. You can still do it. Okay, now because you can break this into 2 linear factors, then we'll do a over x minus 3 plus b over x minus 2. Now notice when I did it, I did the a over x minus 2 plus b over x minus 3. It doesn't matter. It's going to come out the same. It's just that before we had our A equal -1, our B equal +1. This way you'll have the A equal +1 and B equal -1. It works out. But that's what we're having to determine. What is your A? What is your B? So what's the next step that we did? We multiplied everything in every term on both sides by, and I went on and left this in factored form here. I find that's easier to deal with. But multiply that by the least common denominator, which is a factor, x minus 3 times x minus 2. Okay? And when you do that, everything here goes away except the number 1. Everything here goes away except a times x minus 2. And over here, it's b times x minus 3. So that's what you get down here. 1 is equal to a times x minus 2 plus b times x minus 3. I'm sorry. Okay? Now, that's your basic equation. That's what they call the basic equation. Now we're trying to figure out what the a and the b is from that basic equation. Now, it should be true for any value of x, so you get to choose your x. How about x equal 2, x equal 3? Those are two choices. Because that equation is to be true for all x's, you can substitute substitute any convenient values for x to obtain equations in a and b. So that's what we did. The most convenient values are the ones that make the particular factors equal to 0, and that's what we chose. So to solve for a, let x equal 3, and you have 1, that was on the left hand side, is equal to a times x equal 3. 3 minus 2 is 1. So 1 is equal to a plus 0, because when you choose x equal 3, this term goes to 0. You get a is equal to 1. It's that simple. Okay? That's what you do. And that gives you a is equal to 1. You do the same thing, but this time you let x equal 2, and then this term will go to 0, and this will be a minus 1. So your b then, to solve for b, let x equal 2. This will be a 0 here. This will be a minus 1 here. And you have 1 is equal to minus b. So b is minus 1. Okay. So there you found your a's and your b's. Very easy process to do. And once you've done that, I'm sorry, my clip keeps falling off my pocket. It's aggravating, but I'll try to get it to stay up there. Okay. There you found your a and your b. So the decomposition is 1 over x squared minus 5x plus 6 is the same as 1 over x minus 3 minus 1 over x minus 2. Okay, and that's what they just pulled out of the air before. We've shown how to get it by now. Okay. Now, that was example 1, when you have distinct linear factors. Okay. Now, they didn't take it any further. There is a blurb at the bottom of page 552. It says to learn a different method for finding partial fractions. It's called the Heaviside method. There is an article that's given there that you can certainly use as a reference, and if you wanted to write your paper on that one. The idea comes from the book, but the book is not the reference itself. All right, so let's move on to example 2, and this is going to be just a little more involved, and of course, since it's a little more involved, they don't include it in the PowerPoint. Okay, sort of weird how they do that, isn't it? Okay, so here's example 2. Oops, let me go to our whiteboard, and that means I'm going to have to set up and rearrange the whiteboard ever so slightly. So I'm going to scoot the taskbar that you can't see out of my way, and also do the whiteboard in the other direction so I have the most amount of white space to work with. There we go. I think I got it a little too far. Move it up as far as I can here. Okay, that's sort of set up. How are we doing on time? We go to 11:40, so we got plenty of time here. Okay. I may not have time because my head is getting so clogged up. I think I told you all Monday that I was outside a lot over the weekend. We were burning a bunch of stuff, you know, mostly wood, limbs and stuff like that off our con trees that had fallen to the ground. So I breathed a lot of smoke. I was also doing a lot of mowing and all the pollens and things that are in the air in the fall, stirring those up like crazy. And then the temperature dropped and I was outside in a cooler temperature. So I don't know what's caused what, but between the smoke, the pollen, and the cold temperature, I'm congested. Sorry about that. So I might have to pause for a moment, go out and clear my head and come back. So let's see if we can proceed for a bit here. Here is your integral. 5x squared, this is the numerator of the integral, plus 20x plus 6 divided by x cubed plus 2x squared plus x, and then you have your dx. Okay, I hope I copied it right and all's in order. Okay, I'm going to get this heavy book out of my lap. Okay, now the first thing always that you check for when you have rational expressions, make sure it's a proper rational expression, meaning that the degree of the numerator, which happens to be 2, is less than the degree of the denominator, which happens to be 3. And I did not touch the page, and yet it wrote on the page. And other times when I'm trying to write on the page, it doesn't take. Okay, so let me see if I can. Well, I wiped out too much. Okay, I think I'll leave that for now and draw my 2 back in here. This is so aggravating. See, when I want to write, it won't write. And when I don't want it to write, it just writes wherever it wants to. Okay, so there is our deal here. What's the first thing we do? Factor that denominator. Now, we may want to come back and factor the numerator too, because there is a little something they've left out here. Okay, and we'll talk about that in a minute. Okay, but let's all their descriptions, they've sort of left out kind of an important detail. But let's look at that denominator first. Okay, you can certainly factor out an x. Okay, and what does that leave you with? X squared plus 2x plus 1. Okay, now looking at that, you see, well, wait a minute, that's a perfect square trinomial. So this is going to be x times x plus 1 squared. Okay, so there is your factorization of that denominator. All right, now what are we going to do with that? Well, I think I'm going to leave the numerator alone for now. There's a real big part of me that thinks we need to check and make sure that, okay, I can tell you this, x is not a factor of the numerator, okay, because you have just a 6 here that you, well, my pen, right, x can't be a factor. Now, can x plus 1 be a factor? Well, I guess conceivably it could be, but if you tried to do that, you would find out the other factor would have to be 5x plus 6. If x plus 1 was a factor, 5x plus 6 would be the other factor, and that wouldn't work, okay? Because that would not work. So I do that because we can't have any common factors between numerator and denominator. So take my word for it, there's not here. Okay, so what are we going to do then? Well, your basic equation, I guess they called it, would be this then. 5x squared plus 20x plus 6. Now I'm going to write it over the factored form. X times x plus 1 squared, okay, is equal to, okay, now remember what we had? For every linear term, we put a constant over that linear term, okay? So that would be a over x plus b over x plus 1. But because you have multiple terms there, we then, I'm sorry, I've got such an itchy place on my back. Okay, plus, I can't get my pen to move. Come on, pen. There you go. Plus another constant term, c, over x plus 1 squared. Okay, you have a term for this one, a term for that one by itself, and then a term for that squared. Okay, each of these are linear factors, so your constant, your coefficients are to the 0 power. They're constants. Okay. Now, what's the next thing we do? Okay, we multiply every numerator by our least common denominator, which is x times x plus 1 squared. Multiply this one by x times x plus 1 squared. Multiply this one by x times x plus 1 squared. And multiply this one by x times x plus 1 squared. Okay. Now, over here, left-hand side, the x's go out and the x plus 1 squared go out. So this now is what I think they call the basic equation. 5x squared plus 20x plus 6. That's all you got left on this side. And that's equal to, sorry, here the x's go out, and you have an a times x plus 1 squared. Here, one of the x plus 1's goes out, and you're left with a plus b times x from that one times x plus 1, because one of those divided away. And here you have a plus, and here the x plus 1 squared goes out, and you're just left with c times x. Okay, that's now what they call their basic equation. Now, just like before, I'm about to pass out. Okay, hold on just a minute. Should have brought up a backup. Maybe that'll see me through, at least for a little time. Okay. Man. All right. Now remember what we did before? Pick some value for x that will eliminate as much as possible. So why don't we let x equal -1? So that's going to be our first approximation. Let x equal -1, because that's going to wipe out this term and that term. Okay? Well, 5 times the -1 squared would be 5. And then you have minus 20, because 20 plus 20 times a -1 would be -20, plus 6. Okay? Doesn't matter what the x is, 6 is still 6. So that's the left-hand side. The right-hand side becomes, when x equals -1, that goes to 0. This goes to 0. So you're left with minus c. Because x was a -1, you get a minus c. Well, let's add these together. 5 and 6 are 11. Minus 20 would be a -9. So -9 is equal to minus c, which implies, of course, that c is equal to 9. We found our first value here, that c is equal to 9. Now you got to remember where that was, and we're coming back to it in a minute. Okay? The next thing to do, pick another x. This time let x equal 0, because that will wipe out this one and that one. So the next one is let x equal 0. It just doesn't seem fair to do that, but it works. Okay? So here you have a 0 plus 0 plus 6. So you have the left-hand side being 6 is equal to, and when x equals 0 here, you have 0 plus 1 is 1, squared is 1, so you just have an a. You have x equals 0 here, that whole term goes away, x equals 0 there, so here your a is equal to 6. Okay. Now, we've still got to figure out what the b is. You've exhausted all your easy things, so what we're going to do now is plug in and see what the b becomes. Okay, if you know a and c, we should be able to figure out what b is. And this is a little bit of a pain in the neck, but it's doable. Okay, so let's let a equal 6. That would be 6 times x squared plus 2x plus 1. That's squaring that binomial. Plus bx times x plus 1. That's this term right here. Plus 9x. Okay? And that should equal 5x squared plus 20x plus 6. The pen is not writing well at all. Okay. So let's see what we've got. Multiplying through here, you get 6x squared plus 12x plus 6 plus bx squared plus bx plus 9x is equal to 5x squared plus 20x plus 6. Okay, wow, what an expression. Okay, now I'm going to pause for a moment here and drink some water because I'm drying out fast. Okay, once we get this problem done, If I don't feel any better, I'm going to take a quick break and go clear my head because it's harder and harder to breathe. Okay, now here's what we're going to do with this expression at the bottom. If I could find my, there it is. Okay, let's combine like terms. Here we have 6x squared plus bx squared. So basically that means that 6 plus b has to equal 5, because here's on the right hand side, that's what you got. So it looks like to me that b has to equal -1. Okay, now we've got all three of those. Let's just check and make sure this is consistent and it makes sense. Over here on the linear terms, if I could get my pen to show up, that would be 12 plus b plus 9. So let's do 12 plus b plus 9. Those are all your linear terms here. 12x plus bx plus 9x. That's supposed to equal to, if I could read my writing, I think that's a 20x, okay? 20x. Well, let's see. No, we don't need the x here. Is equal to 20, okay? Well, this is 21 plus b is equal to 20. B is equal to -1. That certainly works. And over here we have a 6 is equal to 6, okay? So that works, okay? So your b is -1. So now let's go back to our integral. That's why we left it alone up here by itself. And for some reason the pen just completely disappears. And I don't know where it's gone. Can y'all see it somewhere? Ah, there it is, way down there. Okay. There. Now we got it back. All right. This will be the integral of, now, what is your a here? A was 6. That would be 6 over x dx. Your b was -1, so that would be minus the integral of 1 over, or yeah, let's do it 1 over x plus 1. See, we're doing this. The b is -1 over x plus 1 dx, plus the c was 9. Okay, so that would be 9 times the integral of, and what was that one? C over x plus 1 squared. No, C over, okay, 1 over x plus 1 squared dx. Okay. No, yeah, the 9 out front. Okay, got it. Okay, I'm getting lost here. That's your new integrand. A over x, b over x plus 1, c over x plus 1 squared. C was 9, b was -1, and this one. Okay, I could have pulled that 6 on the outside. I think maybe I should do that. So what does this give us? 6 antiderivative of 1 over x log x, 1 over x dx is log absolute value of x minus the log of absolute value x plus 1 plus, now this one is going to take just a little more work, okay? And I don't feel like doing the work right now, but I guess we'll have to. That's going to be a trig substitution, okay? No way around this. And Let me see if that's right. No, it's not. That's not right. Let's write this as this. That would be plus 9 times the integral of x plus 1 to the minus 2 dx. Okay, sorry about that. That would be 6 times log x, absolute value of x, minus 1 times log of x plus 1, absolute value of x plus 1. And then this will be, if you need to do a u substitution there, let u equal x plus 1, du is dx. I don't know what that noise is, but it was something. And that would then be the antiderivative of u to the minus 2, which would be minus a u to the minus 1. Well, the u was x minus 1, x plus 1, so this would be, whoops, I forgot my 9 there, 9 times x plus 1 to the minus 1. And then you'd have a plus c. Okay, now, here's a couple of other things you can do here. Okay, you can move this 6 inside here, so this would be the log of x to the 6, and since it's raised to an even power, that's always going to be positive, so you can lose the absolute value bars there. And then you have a minus log of x plus 1. I'll leave the absolute value bars in there for right now. Okay, minus 9 over x plus 1 to the minus 1, and then plus c. Okay. Now, you could combine these two terms to be the log of x to the 6 over yuck. I don't think that's going to, I'm running out of room and it's not going to be particularly helpful here. This will be over x plus 1. What I was trying to figure out is, do I need my absolute value bars anymore? I think you probably do, because you want that to remain positive. Okay, minus 9 over x plus 1 plus c. Okay, now let's see how far from reality we wound up here. Okay, log, and they left the absolute value bars in the numerator as well. Log of absolute value of x squared, x to the 6 over x plus 1 minus 9 over x plus 1. You don't need absolute values there, plus c. So yeah, that's how they left it. Okay. They have a little blurb at the bottom saying it is necessary to make as many substitutions for x as there are unknowns a, b, c to be determined. For instance, in example 2, the substitutions x equals 0, x equal minus 1, x equal plus 1 were made. Now, so they did something a little different from what I did. I went on and solved this. They just out of the blue picked a value for the x equal 1 for that, which was that, the b value, and I don't know why they chose x equal 1. It certainly worked, okay, but the way we did it worked as well, okay. And then there's a little technology blurb at the bottom as well, okay. And that requires a computer algebra system. So if y'all don't mind, let me take a quick break. I need to go clear my head. I think I need some more caffeine too. So let's do a quick break. I know we don't have that much longer to go, but we have about 30 minutes, and I think I'm going to need a break before 30 minutes. So let me pause the recording here, and I'll try to be back just as soon as possible. Y'all can take a little break too if you've been sitting. I can't find my cursor. I don't know why it keeps disappearing. Okay, let me see if I can find it on my Wacom. Here we go. All right, any questions on example 2, I believe it was, that we just finished here? All right, now we're ready to go to any questions. Okay, let's go. Yes. Right. Yeah, well, okay. Yeah, when we plugged in the -1 here, is that what you mean? Yeah, well, you plugged it in here and here, and that gave you your C is equal to wherever it was, 9, because you plugged in a -1 here, and that gave you a 5, because -1 squared is 1. And that gave you a -20 plus 6, and when you plugged in here, that wiped out your B, your A here, and it wiped out the B here, so it left you only with the C equal, and put a -1 in for C, for X, I'm sorry, and that gives you a negative C here. I can't talk. Okay, and that's where we got our C is equal to 9. So yeah, we did plug in, but it wiped them out in both places, so plugging again. Now what they did was plug in an X equal 1. We didn't do that. And when you plugged in an X equal 1 and they just pulled that out of the air somewhere, then this would give you a 5 plus 20 plus 6, that would be 31 on this side, is equal to, this would be 2 squared would be 4A, but we already knew what A was. A was 6. So that gave you a, I'll show you. Do you see what's happening? Did that answer your question?
I was asking, since we use -1 on the B part,
yeah,
X on the B X and X plus 1.
Right.
The -1.
Right.
When it counts to X plus 1, we would be times -1.
Okay. You mean right here? If you plug X equal -1 here, is that what you mean? You see where my pen is? You do that, and you get a 0 here. -1 plus 1 is 0. So 0 times -1 times B is still 0. So it wiped them all out. Okay. Now what they did different from what we did, and I'll try to do it quickly here, they use, rather than figuring out what the B is from this one, plugging in the A and C, what they did was just pick another value for X equal 1. And that's a pretty easy one to do. X equals 0, X equal -1, X equal 1. They're pretty easy. This would have given you 5 plus, where's my cursor? Oh, I know what's wrong. Okay. 5 plus 20 plus 6, that would be a 31. Okay. Now this is with let X equal 1. Yeah. But you see, that will work as well. It just gives you slight bigger numbers. That would be 31 is equal to, and we already have figured out what A is, was 6. 6 times 4 is 24. And here we would have had X equal 1. That would be 2 times 1 is 2 plus 2B. And then the C we already had was a 9 times 1, that would be plus 9. Okay, and then you combine like terms here. This would give you a 33. 9 plus 24 is 33. Subtract that, you get a minus 2. 2b is equal to minus 2, so b is a minus 1. So yeah, you come out with the same answer there as we got. Whether their method is easier or short, I don't think, I mean, maybe it took a little less writing, but you still had to do calculations, big numbers, well, not huge numbers, but yeah. So you could do it either way. They just picked up the x equal 1 and then went with that one. Using the a and the b, c that you already had, c equal 9 and a is equal to 6, then using x equal 1, that gave you your b. So it's just another way of doing it. Either way works. Okay. The easy thing was what you suggested, x equal -1, x equals 0. Those give you individually the a and the c. I think, yeah, c and then the a. All right. But good point. Okay. Let's go back to the PowerPoint. Okay. I'm sorry I had to take a break, but I cleared out some head, but I obviously didn't get all of it. Okay. Let's go back to sort of aggravates me. There we go. Okay, let's move on to quadratic factors. This is on page 554. Okay, now when using the method for partial fractions with linear factors, a convenient choice of x immediately yields a value for one of the coefficients. However, when you've got quadratic factors, a system of linear equations usually has to be solved regardless of the choice for x. And that's sort of why I did it the way I did, because you basically are going to have to do it when you have quadratic factors anyway. So here is example 3. Now, hold on just a minute. My head's clogging up again. Let me see if some of this caffeine, bubbly, sugar, whatever is going to clean it, help a little bit. I don't know if it helps or not, but it feels better anyway. All right, so here is example 3. Now, they've been very nice to you, or at least a little nice to you, in that they've already partially factored the denominator. Not totally, but partially. If you had had to do this from scratch, you'd have been scratching a bit, trying to figure it out. They've got part of it. But just as before, we've got to make sure, I'm so sorry, I'm having trouble breathing easily. We've got to make sure this is a proper rational expression, okay? Well, in the numerator, your degree is 3, okay? And why this way? Yeah, there it is. Degree is 3. In the denominator, they've already partially factored it for you, but if you were to multiply for all this, you see you have an x to the 4th power. So the degree of the denominator is greater than the degree of the numerator. You're in good shape. Okay? So let's continue our factorization. Well, we can, in this first factor out an x. X times x minus 1. The second one is an irreducible quadratic factor. You cannot factor a sum of two perfect squares. So this is just going to be x squared plus 4. Now, the other thing that sort of bugs me about this problem is they left the factor of 2 up here. So I'm going to also factor the numerator and put the 2 on the outside and make this x cubed minus 2x minus 4. Okay. Now, that's not really going to help us a lot, but at least to me, it helps a little bit because you don't have to carry around a 2 there. Okay. Now, Let's do our partial fraction decomposition now. Okay, I'm going to leave that 2 here just so you remember it's there. Okay, now the numerator here is going to be x cubed minus 2x minus 4. Okay, I don't think that will factor any further, but I'll leave it like that. Okay, your denominator, of course, then is going to be x times x minus 1 times x squared plus 4. Okay, now we're hoping that's going to be, in fact, let's just remember the 2's there. I don't want to mess with it now. Let's just leave it alone now. Okay, remember it's up here though. Don't let me forget it. Okay, what are we going to do? Well, this will result in an a over x, because that's a linear term, plus this is a linear factor, so that's going to be a b constant over x minus 1. But this one is a irreducible quadratic factor, so therefore its numerator has got to be a linear factor. So that'll be cx plus d over x squared plus 4. All right. Now, what's our next step? Multiply everything in the numerator and denominator, everything on both sides of the equation, every term, by that least common denominator. Okay, so this is going to multiply by x times x minus 1 times x squared plus 4. This is going to multiply by x times x minus 1 times x squared plus 4. This is going to multiply by x times x minus 1 times x squared plus 4. And this one's going to multiply by x times x minus 1 times x squared plus 4. These can take up some room, by the way. Over here on the left hand side, the whole denominator divides out into what we just multiplied by, so you're left with just, and that's why I want to leave off the 2 for now, x cubed minus 2x minus 4. Okay, just what your numerator was. Equal. Over here, the x's go out. And that leaves us with a times a x minus 1 times a x squared plus 4. Here, the x minus 1's divide out, and you're left with plus b times x squared plus 4. And then finally, the x squared plus 4 go out, and leaving you with a plus cx plus d times x minus 1. Now, anyone want to hazard a guess what we're going to do next? Okay, and what you want to put in for x? Okay, very good choice. Okay, let x equal 0. If you do that here, x cubed is 0, minus 2x is 0, you're left with just a minus 4. Why that line showed up there, I don't know, but that's a minus 4. I think I will erase it if I can get my eraser to show up here. Okay. Sometimes it does that. It picks up from wherever I last put something and draws a line to the next thing. Okay, when you put x equals 0 here, what you wind up with here is an a times a minus 1 times a 4 plus, and when you put a x equals 0 here, that goes to 0, that goes to 0. So what do you got? You got minus 4a is equal to minus 4, so a is equal to 1. Everybody follow that? Okay, first part's done. Second part, let's pick another x. Let x equal, anyone want to make a guess? 1. Why not 1? Okay, so what you'd have here then is 1 minus 2 minus 4. Well, that's 1 minus 6. That's going to be a minus 5 is equal to, when you put x equal 1 here, that goes away, and you're left with a b times 1 times 5. And you put a 1 in here, and it goes away. Okay, so you have 5b is equal to minus 5, so that implies that b is equal to minus 1. Now, the question is, what do? We got a c, x, and a d that we have to do for, and there aren't any easy things to do. Okay, now you could pick 2 more values for x, like maybe a minus 1 and a plus 2 if you wanted to, and they would certainly work because you already know the a and the b. So let's see which way the book goes with it. And they chose okay. They did like I do. I think I did. Okay. Okay. Yeah. All right. Let's just use those 2 values we have. A is equal 1, B is equal minus 1. Now they're doing it slightly different because they left the 2 in there. We'll come back to that in a minute. Okay. So okay, I'm still trying to figure out point. You can find the remaining constants by choosing 2 other values of x and solving the resulting equation. Yeah, they use x equal minus 1 and then later it'll do x equal 2. Yeah, okay, I see what they did. Okay, so they pick 1 more x, and this is legal. I mean, it's perfectly fine, just like those were perfectly fine. But now this isn't going to eliminate everything, but let's just use a simple one, x equal minus 1. So here we'll have a minus 1, and minus 2 times minus 1 would be a plus 2, and then a minus 4. Okay, that's equal to, and plugging in an x equal minus 1 here, nothing's going to eliminate here, but let's use our a to be 1 times minus 2, because it's a minus 1 is minus 2, times minus 1 squared is 1 plus 4 is 5. Okay, plus, only let's make that a minus. Okay. Okay. Why did it do that? Okay. All right. Sorry about that. Okay. Now, x equal minus 1, that second term, the b was a minus 1, so that's why I changed that from a plus to a minus. X is a minus 1, so change it back to a plus. And then the x squared would be a 1 plus 4 is 5. Okay. And plus, now here we have c times a minus 1. So that, I'm going to change it back to a minus. And this illustrates why you have to be very, very careful here, because you have so many little places to make errors. Okay, so here we have a minus C plus D, and then you have, let's keep this written like that. Wait, that's not right. Let's make that a minus there. So it would be a minus C plus D, okay, times a minus 1 times a minus 2. Okay, real big pain in the neck here. Now, how are we doing on time? We only got 2 minutes left. This is going to be tough to finish in 2 minutes. So let's see what we've got here. Here we have a minus 5 plus 2 is a minus 3. Here we have an equal sign. Here we have a minus 10. Here we have a plus 5. Here we have a 2. Let's make that a minus 2C plus 2D. I think I did that right. Okay, so that gives us a, when you combine these together, it gives you a minus 5. Add that to both sides, that gives you a 2 is equal to minus 2C plus 2D. Okay, that gives you an equation that basically comes out to be minus C plus D is equal to 1. Okay, that gives you one equation. Minus C plus D is equal to 1. Now let's do another one. Let x equal 2. And I don't have enough room to do this. And I don't think we have enough time to do it. No, we don't. So do you want to finish this on your own, or we'll finish it in class on Monday? What you think? I wish I hadn't had to go down and class on Monday. Okay, so we will pick up. We've gotten the minus C plus D is equal to, okay, now they have 2, we have 1, and there's a reason for that. We factored out the 2. So we will go for the second equation there and go from that point on. So let me erase my marks here. Okay, and homework exercises here. We made good progress here, but sorry I had to take a break in the middle. Do any of the odds 3 through 19. They're all at Calc Chat, 7's at Calc View. Either 21 or 23, they're both at Calc Chat, 21's at Calc View. Any of the odds 25 to 31, they're all at Calc Chat. Let me see before I go too much further here. We haven't done any with definite integrals, so maybe just stop at 19 and we'll do some definite integrals next time. So stop at 19 and we'll go from there. All right, any questions? Sorry I had this break in the middle there, but I was just having trouble breathing. Okay, sorry about that. So let me stop the sharing here. Still having trouble breathing. And we'll end the recording unless you have any further questions. Anything else? All right. Take care. Have a safe weekend. Be careful, folks. The counts are going up, 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 up. So be careful. It looks like it might be a pretty weekend. Be careful, okay? And we'll see you on Monday, okay? Take care. Bye-bye.